All right, guys, let's take a look at this problem. We didn't quite finish this one in class. I'm just going to restart it. I'm going to skip over the implicit differentiation part. All right, so if you're struggling with that, come and see me. All right, make an appointment to see me after school. So I'm going to skip over that part because this is more of an application of the derivatives versus like learning how to do implicit differentiation. Okay, so I kind of want to show you the concepts a little bit better than I did in class today. All right, so let's just read the question. For what values of x will the curve, and I have some random curve, have a horizontal tangent line? Show your work and explain your thinking. All right. So let's take a look at the curve. Okay, this is a very bizarre looking curve, so it's not a function. That's why we're saying curve. Wouldn't pass the vertical line test, which we expected. And that's why we have to implicitly differentiate versus normal differentiation. Right, so we kind of expected this, so some kind of crazy looking curve. All right, so what is the question? The question is, where is there a horizontal tangent line as far as this function? All right, typically, horizontal tangent lines, my sister just got home, horizontal tangent lines occur at maxes and mins, okay? So if I look here, if I was to zoom in, I'm going to zoom into this piece of it. Let me get rid of some of this chaos here. If I zoom in, it's a lot more clear now. If we just kind of section off this curve, this looks like a min. In fact, it is a min, right? It's a local minimum. And that's where the derivative would be 0. That's where you would have a horizontal tangent line, right? The slope of the tangent line at about negative 0.8-ish, maybe a little more, maybe a little less. That should give you the horizontal tangent line, all right? So our answer needs to be somewhere close to negative 0.8, right? That's what we're after. That's where we're trying to find. And if I take, maybe zoom out again, it appears as though there's a second one, right? This looks like a local maximum if I start to zoom in. Right? So at some point over here, at the top of this little hill, there should be another horizontal tangent line, right? Where the derivative is going to be 0. And that looks like, I don't know, like 1.7-ish, somewhere in that region, okay? So it looks like we're trying to identify two answers. There's two spots where there's going to be a horizontal tangent line, and we're going to have to use the power of calculus and some pre-calc and algebra 2 knowledge to be able to figure this out. Okay, I want you to recall that we've done this before. Okay, it was a little easier because the x values came right out. It's a little harder this time because now we're dealing with x's and y's. So let me show you how we use calculus to figure this stuff out. Okay, all right. So of course the first thing you do is find the derivative, right? That should be the first step, and I think everyone's okay with that. I'm just going to jump right down to dy dx. I think we did this in class anyway, and if you're struggling with this part of it, then just let me know. All right. So this is what we got for our derivative. And then I kind of set you free, and then you're plugging things in the calculator, and then we kind of ran out of time. So let's see. Here's our derivative, and let's go back to remind ourselves of the question. So I want to know, where does this have a horizontal tangent line? Horizontal tangent lines occur when dy dx, okay, or the derivative, is equal to 0. Okay, now let's take a second look at this derivative. This derivative is a fraction, okay? It's written as a rational expression. So when is this entire derivative, the whole thing, going to be equal to 0? Well, if you're dealing with a fraction, that's when the numerator is 0, right? So when this is equal to 0, the top, the entire value of the fraction will be 0, right? And if the bottom was 0, then you get an undefined value for your derivative. Okay, and that's going to happen in the next problem. But right now, we only care about where the derivative is 0, and that's going to be where the numerator of the fraction is 0. So we're going to say 4y minus 3x squared is equal to 0. All right. Now, earlier in the year, you would have had this derivative, and it would have all been in terms of x. So you would have been able to solve it for x or factor it, use a calculator, but essentially we're trying to find the x values, right? That's what we've always been trying to do. What's difficult about this one is that we're not going to ever be able to isolate x using basic algebra, right? So this expression here has two unknowns, so we're not going to be able to solve it. So I think someone in class mentioned a system. All right, and that's exactly what we need to do. So recall that the x values here are the same as the x values here, right? We just, as calculus students, need to know how to interpret these x values, right? So when I solve for this x, right, if I can get the x values out of this, that's going to be where the original has a horizontal tangent line, right? Remember that the x value in the original function is related to the derivative of that x value, right? That's how we find the location. They're inherently related, the function and the derivative. So I'm trying to find the x values now. How are we going to do this? Well, all we're going to do is substitution, okay? So I can't isolate the x, unfortunately, but what I can do is I can solve it out for y and then plug it into the original, okay? And then we can try to work with that one. So let's do this. Let's solve this for y. That should be no big deal. That's just 3/4 x squared. And now I'm going to take this and create the system, all right? But it's going to work with the original. So anywhere I see y, I'm just going to plug that right in. So it's going to be right here, and it's going to be right here for this y. Okay, and then we're going to see if that's a little bit easier to deal with. And it should be, because I'm going to have a new equation that only deals with x's. All right? Okay, so let me get rid of some of the stuff here that we don't need anymore. So we're okay with this. We have this solved out. Again, we're trying to find the y's. We're just running into some problems. I mean, we're trying to find the x's, but we're running into some problems because we have multiple variables. So let me just start to replace this here. All right, I'm just plugging it in. So we have x cubed, that's going to stay, plus 3/4 x squared, quantity cubed, equals 4x times 3/4 x squared, and then we'll tack on the +1. Now, it really feels like that wouldn't be helpful. Like, how that looks more complicated than what we started with, right? But what can we do? We can try to identify the x-intercepts of this, right? So now we need the power of technology, all right? So what I'm going to do is I'm going to basically set this to 0. So I'm going to move everything over. But before I do that, let's clean this up. So what do we have? X cubed. Let's deal with this nonsense here. What is that going to be? 3 cubed is 27. 4 cubed is 64. X squared cubed is x to the 6th equals, well, these 4s would cancel, I believe. And then we're going to end up with what? 3x cubed plus 1? Yeah, and I'm just going to move the other guys over, and I'm going to also put it in standard form. So the first term, the leading term, would be 27 x to the 6th over 64. Just using some basic algebra here. So what would come next? You have x cubed. We have to take away those 3. So what is it? Negative 2x cubed. And then minus 1 equals 0. Is that right? Okay. So at this stage, you'd put this in the calculator. All right, and this is kind of where we left off. Some people got it, some people didn't. But let's use Desmos. Okay. So let's plug this in. This is the graph of what we just wrote down. All right, if the original function at this here, okay, at this particular value, all right, which was related to the derivative being set equal to 0. We plugged it into the original so we can solve for the x values, all right? So now we've got the function in and of itself. So this should tell me what the zeros are, if I just touch it. Okay, there we go. So negative 0.769 or negative 0.77, all right? And then the other one, we were expecting it between 1 and 2, right? So let's see here. This is the x value. We have 1.732. Okay, so those are going to be our 2 x values in the original function where we have a horizontal tangent line. All right, so that would be x equals to, what was it, negative 0.77, and what was the other one, 1.732, I believe. Yeah, let me just double check so I don't screw this up. 1.732, yeah, okay. All right, and if we go back, that's pretty much in range with what we were expecting. Let me pull back the original. So we were expecting something close to negative 0.8. It was actually negative 0.77, so that makes sense. And then back over here, we were expecting something a little less than 2, and 1.7-ish is about right. Let me zoom in to the top. Yeah, 1.7-ish is pretty close. All right, so that's how you handle that problem. That's a tough one. Okay, that's a really tough one. What you should do is try this problem over. So get a blank sheet of paper, try this problem, start it off. Someone's calling me. It's probably my sister. She's fine. Who cares? Cover this stuff up and try to do it on your own. Go through those steps. Try to make those connections. All right. The second one isn't as intense just because the way I wrote it. So in this one, it says in terms of y, describe the values of x for the curve having a vertical tangent line. All right, so if I go back to the derivative, that's where the denominator now would be equal to 0. So what was the derivative? 4y minus 3x squared over 3y squared minus 4x. But I don't really care about the top because we've already dealt with that. This is where you would get a undefined value for your derivative, which indicates a vertical tangent line. Okay, so vertical tangent lines occur at dy dx being undefined. All right. Now, this problem you don't have to do as much work just because I wrote it in I want you to give me the x values in terms of y, so I don't want any numbers or like exact values. So all you got to do is take the bottom, set it equal to 0, and now you can just solve for x. All right. Now, if I wrote this problem like the first problem like that in terms of y, then that would have been a lot easier. But when you have to find the exact location, that is pretty intense. All right. So to get a vertical tangent line, it's when your denominator is equal to 0. So we just set it equal to 0, and we're just going to solve it out for x. All right. So when you isolate the x, you should get x equals 3/4 y squared. And my sister's calling me again, so I got to go. All right.